Students, welcome back. This is the part B of today's class, and let us start where we had stopped. We had seen that we had talked about the quantum properties of nuclear states. We looked at two things: the energy of nuclear energy levels. Then we went on to study the nuclear angular momentum, which is denoted by capital 1. And now we have the parity. So let's see what is parity of a nucleus. Earlier we have talked about parity of nucleons, that is the particles inside the nucleus. Now we are going to talk about parity of a nucleus. Actually, if a particular nucleus consists of n particles, then summation I over n, that means this, if this is a positive quantity, then we say that the parity is even parity, and if this is negative, then it is said to be odd parity. So earlier we had seen that different particles, they have got individually, they have got parity, so we add them up. If it's an even number, it's even parity, and otherwise this is odd parity. Now after that we move on to isospin and then statistics. So what is isospin and statistics in case of a whole nucleus? See, students, please keep in mind that in the last class we had done these properties for individual nucleus. Now we are looking at a nucleus as a whole. So actually isospin, when I speak about isospin, then for a given nucleus, the isospin is generally denoted by T3 or Tz instead of T. So T3 for a nucleus is equal to minus half n minus z, and this n minus z is also called the neutron axis. Why neutron axis? Because you see in lower atomic number elements, the number of neutrons is equal to the number of protons, but as the atomic number z increases, it is found that n increases, and so we have a n minus z. So T3 is given by the of a nucleus is given by n minus z. So that's quite easy to calculate if you know, once you know the n and the z. Then the remaining quantum property of the nucleus is statistics. We have talked about Bose-Einstein and Fermi-Dirac statistics in case of particles. Now in case of whole nucleus, you see it depends upon A. For odd A, we have that find that the nucleus obey Fermi-Dirac statistics, which is quite obvious because you see, if A is odd, that means A is equal to twice n plus 1, and since all nucleons have a spin of half, you multiply by half. This is a half integer multiplied by half, multiplied by this is an odd number multiplied by half. So this quantity obviously is a half integer. Suppose I take lithium 7. In case of this, we have what would be the number of particles, total number of neutrons and protons, it is 7. So 7 into half is equal to 7 by 2. So obviously it is a half integer, and so it will be a Fermi particles. So it is a fermion, and it is obeying Fermi-Dirac statistics. Similarly, when A is even, then A must be equal to twice n, and then that multiplied by half will be the number of particles, the total spin. So this is equal to n, which will definitely be an integral spin. The integral spin gives Bose-Einstein statistics. So we come to know that when A is odd, the nucleus obeys Fermi-Dirac statistics. When A is even, it follows the Bose-Einstein statistics. So these are some of the qualities, and I'll share the study material with you, and I'll be sharing materials from your book Nuclear Physics by D.C. Tayal. So I'm not able to download a soft copy of this book, so please try if you can. So this is a standard book, and we are following this book. So this is all about the quantum properties of the nucleus. Now we move on to something else, that is the nuclear magnetic dipole moment. Now what is this? For this we look at the nucleus. We will talk about the nuclear magnetic dipole moment. So now talking about the nuclear dipole moment, we know that a nucleus consists of protons and neutrons. Of these protons are positively charged particles, and we already know that these particles, they spin about their own axis. So you see that a spinning particle is like a particle in a circular motion is like a current. It means if it moves in a circle of radius r, suppose. So you see this is a charged particle, proton is a positively charged particle, so obviously it is equivalent to a current. So charged particle in motion is a current. So we know that when there is a current flowing in a circular path, then this acts like a magnetic dipole. And what is a magnetic dipole? Magnetic dipole is a very short magnet where the length twice L is very small, and this side, one of the sides is N, the opposite side is S. And what is N and S is determined by the direction of current, and we generally look at like this. If you write the N in this manner, this is N and this is S. So when you look at a face of the coil, the side which looks this way, look at this, is this not anti-clockwise? So that side will be not. So for us, this front surface is the current is flowing in the anti-clockwise direction, so this must be the north pole. And if you look from the other side, you will find, just imagine yourself standing on the back side of this coil. So you will find that for that side it is a clockwise direction, and that side will be south pole. So if I imagine a very short magnet, I have just decreased this length. So this is a dipole. So one side, if it is like this, this is the north pole, and the other opposite is the south pole. So similar is the case of a proton. Proton is a charged particle, it is moving in a circular path, so it will give rise to a current. And a current moving in a circular path acts like a magnet. And magnet means a very short magnet, that is a magnetic dipole. So that means proton moving in circular path is equivalent to a current flowing in a circular, we may say wire or something like this. That implies a magnetic dipole. That means this also acts like a magnetic dipole. And then what is a dipole? Dipole is just a very short magnet. And in a dipole, like a magnet, we know that when you have a magnet, you see I drew it circular just to show that its similarity with this coil actually. So whether it's a magnet, whether it's rectangular, even if it's rectangular, we can call it a dipole if it is very short, if this length is very short. So here one side is N, the other is S. Now we associate a quantity. We all know there is a quantity called M, which is called the dipole moment, or if I want to be more specific, I'll have to say that this is the magnetic dipole moment, and this is equal to twice L into M. Twice L is the length multiplied by the pole strength, so this is twice ML. So this is twice ML. So if we have a circular coil and that acts like a magnet, in that case, since we don't have this M and this L, what do we say? We say that the magnetic dipole that arises, this quantity that arises due to a charged particle or due to a current flowing like this, is equal to, we show it to be denoted by mu, and mu is equal to I into A. So that is the magnetic moment IA. So now we know that with the motion of a particle, charged particle, and in our case we consider the proton, there is a magnetic moment because of its rotatory motion. And it has been found that it has got two types of motion. One in its around its own axis, which gives rise to, because it is spinning, mu s, and then again around an orbit also, it also moves in an orbit, so it gives rise to mu L. So we have the orbital dipole moment, magnetic dipole moment, this is the orbital, and the spin magnetic dipole moment. So this is about the magnetic moment of a proton. Now on measurement, it has been found that the proton also has a magnetic moment, and that is the most strange thing, because we know that a proton is an uncharged particle. So how come it gave rise to a magnetic dipole moment? But the measurement shows that yes, it has got a negative dipole moment. So we'll talk about it in our part C of our class.